2000. All right, it's a pleasure to introduce Chris Murphy, for those that haven't met him. Chris is a lecturer at the University of York in the Department of Physics and the York Plasma Institute. He's one of the leading high-power laser experimentalists in the UK. He's also a friend, and if we get that paper finished, a collaborator. Chris got his PhD in 2007 from Oxford, although he was based at, from Imperial, though you were based at CLF. And then you had postdocs in Oxford, Ohio, and CLF, where you worked on lab astrophysics, X-FEL, some nuclear physics, for going for a fellowship in Edinburgh, and then moving to York 2 years ago. Please.
Thank you very much. Yeah, so it is a pleasure to be here. I have a sinking feeling the only reason I was invited is because today's St Andrew's Day, and you wanted the Scotsman to be presenting on St Andrew's Day, but I'll take it anyway. I'll take the invitation anyway it comes. So yeah, so this is the University of York with our beautiful lake. We also have a fountain. So I'm going to talk a little bit about laser plasma interactions at the intensity frontier. And I thought, I've kind of done different versions of this talk, and I try and tune it to the audience. And sometimes it works and sometimes it doesn't, and if it hasn't worked, I apologise, but we'll give it a go. So this kind of work has to be done in massive collaborations. The next scale facilities we'll be using are facilities like the LINP facility in Romania, which it's going to cost about 360 million euros. And so you can't do this kind of science alone, and so there's necessarily a whole bunch of people. I'm not going to go through them all, but needless to say that this work is not just the work of one individual, and certainly not entirely mine. So I'm going to start by talking a little bit about lasers. I'm going to talk about what I mean by power, what I mean by intensity, and try and explain a little bit about the scales I'm going to be using. I'll then talk a little bit about what science we can do at the moment, and then I'm going to say a little bit about what I mean by ultra-intense lasers and where this intensity frontier is taking us. Some huge big monsters that lie beyond the fringes of our current capability, and how we can use current facilities to try and discover a little bit more about what lies in that kind of unknown region of intensity space. So lots of lasers come in different shapes and sizes, as do laser facility users. So everything from this laser pointer here all the way up to this is the Gemini facility, and this is a bunch of us working on the Vulcan petawatt. So this target area you can see relative to the standard human is about 3 meters by 1.5 meters by 2 meters is the target chamber. The actual laser itself is a little bigger than twice the size of this room. That's a fairly small laser. This is the Vulcan laser, it's about 4 times bigger than that. So they're large facilities and they reach high intensities. What kind of facilities do we have at the moment? What kind of intensities are we talking about? Well, when I define, I'll first of all define peak power. And by peak power in a laser, I mean the total amount of energy contained per pulse divided by that pulse duration to give a value in watts. And the kind of powers I talk about, the lasers that I've used, tend to be in the terawatt, that's in 10 to the 12, or the petawatt, 10 to the 15 watts. Is roughly the range that we're talking about. These are kind of colour-coded and shape-coded for types of lasers. So you have nanosecond scale lasers here, that you need something like a megajoule of energy in a nanosecond in order to get to this petawatt line. For picosecond systems, you need about a kilojoule of energy, and for titanium sapphire systems, or femtosecond systems, you need tens of joules in tens of femtoseconds. And so you can use any of these three systems and still get up to a petawatt peak power. So what do we do with these lasers? Well, it depends how much energy you have. And the argument I like to make is what you need depends on what you want to move. If you want to move electrons, you don't need much energy, so you can make do with these femtosecond systems. If you want to move ions, they're a bit heavier, so you need a bit more energy, so you need to put that energy in over picoseconds so the ions have time to move. If you want to actually move material, if you want to launch shocks, if you want to simulate supernova explosions, if you want to compress capsules and you do ICF, then you need to move bulk material, you need to move milligrams of material, and so you're going to need nanosecond systems. And this is a photograph, an actual SLR photograph of two shots colliding. That was an experiment we did on Vulcan. This is some ion acceleration, And these are some X-ray images taken using X-rays generated by femtosecond systems. So, what do the lasers themselves look like? This is 10 for gratuitous laser pictures, which Anton assured me that would go down well. So this is half of the National Ignition Facility in California. This is 96 beams out of the total 192 that make up the facility. The facility cost about €6 billion to build back in 2002 time. And what they do over there is they take these nanosecond long kilojoule style lasers to focus megajoules of energy onto about a square centimetre in order to compress capsules and try and make fusion energy work. The capsules go inside, this is the target chamber, it's the top third of the target chamber. The full target chamber is a big sphere. So this is the top third you can see, and it's about 10 metres in diameter in total, the target chamber. The beams come in through these square ports, and the diagnostics look through the circular ports. If this looks at all familiar to you, it may be because it was also the warp drive in Star Trek Into Darkness, which is kind of nice, a nice aside. And another aside is it takes me 3 months to get security clearance to go on site at Livermore, but if you've got a Hollywood camera crew, you can get in about a day and a half. So this is more like the kind of lasers that I use. This is Astro Gemini, target area where we're currently doing experiments at the moment. So we talked about lasers are big. You get powers of 10 to the 12 or 10 to the 15 watts. What does that mean in terms of intensity? Well, if you've got a certain power, you want to get intensity. In laser plasma physics, at least, we define intensity to be the energy per pulse divided by the pulse duration in the focal area of the spot. And so, for example, and I've just done this is like my version of theory. I basically calculate the spot area based on a certain diameter. We tend to focus these lasers down to something between 1 and 100 microns. And this means, for example, if you've got a petawatt laser, which is 10 to the 15 watts, and you focus it down to a few micron spot diameter, you get an enhancement of 10 to the 7, so this becomes 10 to the 22 watts per square centimetre. So if I talk about high intensity lasers, I'm talking about something like 10 to the 20, 10 to the 21, 10 to the 22 watts per square centimetre. And the maximum available today is about 10 to the 22 watts per square centimetre using these kind of numbers. So we've got intense lasers. What does that mean? Well, to recap exactly what we mean by these laser systems, for high power we need short or ultra short pulses, and for high intensities we need small focal spots. And currently the limit of our technical capability is about 10 to the power 22 watts per square centimetre. And this is achievable both with picosecond and femtosecond systems. So the big question is why? And it's a question that I get asked an awful lot from the other side of our community and for engineers and people like, why do you actually want to study this? So partly it's interesting for pure physics, but partly there's lots of applications. So one of the things that people are really interested in is the fact that by focusing lots of energy into a small space, you can make extreme fields. And these extreme fields could be used to accelerate particles like electrons, accelerate ions, and possibly find some miniaturization of accelerators so that you could, we can't get to building a mini CERN or anything like that, but you could imagine building, a tens of MeV or hundreds or GeV particle accelerator over the space of a few centimeters. And a lot of the things that we're interested in, for example, ion acceleration at the moment, which is kind of lagging behind electron acceleration a little bit presently, would need higher intensities. And so you want to see what happens when can we just keep on increasing the laser intensity, and can that allow us to make a particle accelerator that can do hadron ecology, can make a carbon beam that can irradiate tumours and try and do cancer therapy. Well, maybe, but we need higher intensity. And so if we want higher intensity, does that just come as a linear increase with all the physics, or do we have to consider a little bit more about how things change as you start increasing the intensity? And so I'm not going to talk too much about the critical field in QED because there are many people in this room who know much more than I do, but I will talk a little bit about how the QED relates to laser intensity. I'll then talk a little bit about radiation reaction, stole shamelessly from Tom Blackburn at Plymouth University. His description is a good Compton experiment about how you consider radiation reaction. And I'll finish off by showing some experimental data that we took in order to try and understand what might happen at next generation facilities. And this is very much work in progress, so there won't be any great conclusions about huge revelations in physics, but there will be a plan ahead for how we can try and understand extreme physics a little better. So I'll introduce a quantumness parameter called chi, and this I'm going to define as how strong the laser field is in terms of the electric and magnetic fields relative to some critical field. And this critical field I'll use is often known as the Schwinger limit in QED. It's basically, you can calculate it in many different ways. You can see it's the work done, it's the energy, the field required to do work of the rest mass of an electron over a Compton length, or you can say it's the field at which virtual particles will be accelerated onto the mass shell. So there's lots of different ways of doing it, but another way of calculating it is if you just think of any fundamental constants you can, like h bar and e and me and things like that, and you put them all together in order to take units of electric field, you end up with this critical field in QED, and it's on the order of 1.3 10 to the 18 volts per meter. And so the question is, how close is this laser field to reaching this critical field in QED? When do we have to start worrying about critical fields in QED? And it turns out slightly earlier than you'd think, because from the frame of a moving electron, this criticality dimensionless parameter is reduced by a factor of gamma. And so it turns out that if you've got a moving electron, it sees these quantum effects at a lower laser intensity than would be for a stationary electron. And it turns out that if you hit an electron with an electromagnetic wave, you automatically start oscillating the electron. And so if we want to consider how close to some quantum limit we are with a laser-plasma interaction, we not only have to consider the strength of the electric and magnetic fields of the laser, we also have to consider the velocity of the electron, or the energy of the electron as it's oscillating. Now, for a simple stationary electron being hit by a laser, the gamma that can be reached by that electron is simply what we call the dimensionless vector potential or the normalized vector potential of the laser A0. And this basically, you can describe it in different ways, but the way I like to think of it is it's the gamma reached by an electron in a single cycle of a particular laser intensity. And that basically means the electron goes faster if the electric field is stronger, so if the intensity of the laser is higher, A0 goes up. And also, if the frequency of the laser goes down, the A0 goes up. And this can be thought of simply because the electron will continue accelerating in the same direction as long as the phase of the wave is positive. And so if you make the wavelength of the laser longer, the electron will be accelerating for longer and will reach a higher velocity. And what velocity is that? What energy is that? Well, that's defined by the A0 of the laser, which is a function of both the energy and the electric field, the intensity, and the frequency of the laser. And so we can take all these expressions and we can say, well, okay, for a reasonable laser system, what intensity do we have to reach for this chi to approach something that becomes important? So say, well, we can say that the chi is proportional to A0 if we say this gamma is simply the A0 of the laser. And if we say that the electric field strength in the laser is simply the square root of the laser intensity, and remembering that A0 here is also proportional to the square root of the intensity, that means that chi must be proportional to I to the first power, right? So it's linear with I. And you find that chi reaches something like 0.2 when the intensity of the laser reaches 10 to the 23 watts per square centimetre. So that's interesting because it means that our simple picture of how electrons interact with lasers is going to break down in some way, or we're going to have to consider new terms and new effects when the laser intensity exceeds this number. The good news is we're not there yet, right? So this laser doesn't exist, and so we'd like to think we don't care about it. The problem is that currently in Europe we're spending about €1 billion building new laser systems which will reach this, and we haven't quite worked out whether or not this is going to be a problem for the applications of that laser. And so it's something that's quite timely, it's quite urgent. We really start working out what this means. And that's partly by getting clever theorists like Anton and Thomas and other colleagues. Or it's also about pinning down all the different theories that possibly exist about what could happen in this strong field QED limit by doing experiments and trying to work things out. But we don't have the laser. What will happen when we get to that laser intensity? Well, there's some simulations done by Chris Ridgers, and you can argue about whether these are correct to a fraction of a percent, or correct to 10%, or not very correct at all. But the point is that when you start oscillating electrons in the electric field, they start radiating. And for an intensity of about 10 to the 23 watts per square centimetre, these simulations seem to show that 10% of laser energy gets turned into gamma rays or X-rays, depending on whether you're an astronomer or nuclear physicist. But hard photons, one way or the other. At 10 to the 24, it becomes a significant fraction of the energy is just being turned into hard photons. Now, that could be interesting because it means that when you focus these lasers down to ridiculous high intensities, you end up with this very beam-like gamma rays, and you possibly end up with big floods of positron-electron pairs flying out, and you could do some interesting astronomy with it. But the point is, if you want to couple energy into this foil in order to do acceleration of carbon ions for oncology, you'll find you're not coupling any energy into the foil anymore, you're just turning all the energy into gamma rays and it goes straight through the foil. And so we need to really understand a little bit more about this. But as I say, we don't have lasers that can do this. So how, as an experimentalist, it's fine, I mean, theorists, and I don't often say this, but somehow have it easy that, you know, you can just make up a laser in your, either your equations or your simulations, which allow you to study something that doesn't exist. For me, I need something that exists in order to use it. So the question is, how do we study these quantum effects realistically without having a laser that reaches those intensities? And the answer is back in, well, a quick aside into classical quantum radiation action. This is going to come into it, and this turns out to be related to this chi parameter that I spoke about already. And it's one of the, I found throughout, I mean, even since undergrad, in fact, even since doing physics at school, I found that as soon as I learned a little bit more about physics, I realised that everything I was taught before was just kind of right, but not exactly right. And I think this has never ceased to be true. And one of the big things that kind of dawns on you, and again, this isn't anything difficult theoretically, it's just something that we all get taught, that an electron in a magnetic field has a circular motion, right? It just goes round and round in circles forever. And then at some point in a different physics class at school, I was taught that if you accelerate particles round in a curve, they emit radiation. And I never in my mind put those two things together and realised they were inconsistent. Because the truth is, this bending must release photons, and therefore this particle must lose energy. And therefore, and in fact, you can calculate using just a synchrotron equation what the power radiated would be. And the problem with this image is that this doesn't conserve energy. You can't have an electron emitting some power as it radiates without and then continue in this same path. And so the truth must be something more like this, where as the electron radiates, it slows down and slowly curves towards the centre as its radius and curvature decreases. So if this is true, then basically you need an extra term in this equation of motion, and this is known as the radiation reaction force. And if you use this synchrotron power in order to define what the force must be, you end up with some force, I'm not going into details, but it basically allows you to compensate for the equation of motion of an electron using the force of this self-radiated emission. Right? So if the electron radiates, it must slow down, and actually you also have to conserve momentum as well, right? It has to move in a different direction because it's emitting a photon. And so this is a simple case of the constant magnetic field, but it must also be true for an electromagnetic field such as a laser plasma interaction. So how do we deal with the fact that this is an effect which is going to become important? Well, we can try and measure it. So we can look, so this is more work by Tom Blackburn, who looked into what happens to, if you think about a classical radiation spectrum for an electron in an electromagnetic wave. And you can consider this as being the laser interacting with the electron and Compton scattering from the electron, if you want. And therefore, because the electron's got some gamma, when the laser Compton scatters from that electron, it gets upshifted and you end up with some photon spectrum where the laser is basically taking some energy from the oscillating electron. And if you do a sort of a classical calculation, you find that when this chi factor, this quantumness parameters that I've got, is considered the energy released, the energy spectrum of the photons released in this interaction as a function of the initial electron energy looks like this. And so you see that, for example, when chi is 0.1, most of the energy emitted by an electron of say 1 GeV is round about the 50 to 100 MeV. And that's fine. So that means that you can understand if you've got a field of strength 0.1, an electron of a GeV energy, you'll get a photon spectrum out that looks like this shape, and it'll have a peak round about 50 to 100 MeV, and everything's fine. But what happens when we increase this chi parameter to higher values? You get these two graphs here, for a chi of 1 and a chi of 10, and this is obviously problematic because in these regions here, you have an electron of energy 1 GeV emitting a whole bunch of photons with an energy 1.2 GeV. Right? That's not physical, it can't happen. So what's happened? Well, the answer is that this whole process has become quantum. You have to consider it non-classically in order to get the right answer. In fact, and it's not just a small correction, but actually if you do a semi-classical solution, you find, well, this all has to disappear. I've put in, I'm still not too sure why I include this, because this is something that you've probably heard Anton talk about before, I guess. And so the exact solution is, I can't spell Feynman apparently, but never mind. You can, to get the real solution, to actually calculate exactly what's going on here precisely, you have to use at least 3 Feynman diagrams. And there's arguments about how many you actually have to include. Is that number gone up or down recently?
No, it's the same.
It's about three So it becomes really difficult and really complex. In fact, it's quite intractable to calculate. You can do it for a constant magnetic field. You can do it for a plane electromagnetic wave. If you do it for a plane electromagnetic wave, you end up with Volkov states. So this is too much, right? This is something that we can't really understand, and not only that, but we don't really know how far we have to go because it's difficult to generate experimental data which understands this. And so how do we do it? Well, this is the slide that I showed before, where basically we defined that chi becomes close to 1 when the intensity of the laser reaches 10 to the 23 watts per square centimetre. We said we don't have lasers that can do this, so how are we going to understand like next generation lasers? The solution is, well, here we assumed the only thing that gave the electron its gamma was the A naught of the laser. So the only reason that the electron was relativistic was it was oscillating in that electric field of the laser. Turns out that you don't have to do that. We could come up with a situation where instead of hitting a target and letting the laser oscillate the electrons at some gamma, we could have an electron beam travelling the other way with a higher gamma and hit that with the laser. And if we do that, instead of having this, we can now replace this gamma with a pre-accelerated electron bunch, so we no longer wrap these two terms into the intensity of the laser. We can now separate them and say that for if you've got a gamma of 1,000, so an electron beam with an energy of about 511 MeV, and an intensity of the laser of about 10 to the 21 watts per square centimetre, so a laser that actually exists, then we can have a chi of about 0.1, and we can start trying to understand and measure some of these Compton scattered spectra, which tell us a little bit of information about the strong field QED that's going on in these interactions. And hopefully, this will help us understand what will happen in next generation facilities where the laser intensity is higher. So that's exactly what we did. So it turns out that, for example, the Astro Gemini laser system that I showed before, where the target area is about the size of this room, it can reach intensities of between 10 to the 20 and 10 to the 22 watts per square centimetre. It can accelerate electrons up to a GeV, and so this green box represents the sort of the space of intensity and gamma accessible by this one laser facility. And it turns out that if you get an intensity of about a few 10 to the 21 watts per square centimetre, and an electron gamma of a few 10 to the 3, a few thousand, you can actually hit the chi of 1 successfully. And it turns out this is a really difficult thing to do, and the data becomes really messy, but at least we thought, well, let's give it a go. And so we did this experiment at the Gemini facility. But to understand how we do that, we need to generate an electron bunch from a laser. We do this by weak field acceleration. And this is probably something that in other seminars I tend to gloss over. I'll try and do a little bit of detail. It's quite, the simple picture is very simple. The truth is a lot more complex, but let's just stick with the simple picture at the moment. Basically, if you imagine a boat travelling through a lake, and it's a still lake, and as it's stationary, the boat displaces a certain amount of water. And as the boat starts moving forward, the lake compensates by filling in the gap where the boat once stood. Now the water just doesn't all of a sudden push in and remain perfectly flat, it overshoots. And so you end up with a peak in the water directly behind the boat. And this happens as the boat travels along, you end up with this wake. A wave travelling behind the boat, and this is the wake. Now the same thing happens when you fire an intense laser through a plasma. If it's a short pulse, as in femtoseconds, the ions don't have time to move. And so all you're doing is swishing around the electrons. And as the laser passes through, you end up with a wake behind, and this is known as the wake field, because it creates strong electric fields behind. And these fields can reach hundreds of gigavolts per meter. And so you end up being able to accelerate particles to a GeV within a few centimeters. And so this is the description given by Tom Katzleis in a Nature article about 12 years ago now, where the laser travels through. You end up with this wake behind, and at some point the wake grows so strong you get a white water in this sort of surfing analogy of electrons behind that fall into this wave, and they feel this accelerating gradient down. In the laser case, this is an electric field caused by an excess of electrons here and a depletion of electrons here. And you end up with some monoenergetic beam of electrons traveling on the outside. And so my PhD students run a little simulation to show this, and what you'll see. Sorry? Oh. Yeah. And so what you're going to see is you're going to see a simulation box with a laser travelling from left to right. The colour scheme tells you the density of the electrons, and I'll point out the laser when it arrives. And as the laser reaches the left, it travels from left to right, as it reaches close to the right-hand side of the box whole box will start moving along with the laser, so we don't have to simulate too large a region. And you'll find, and you'll see what happens. So we've got the laser, which is this thing here, travelling from left to right, and you can see this periodic wake structure behind. At some point, the intensity of this bunch this electron population becomes so intense that some of the electrons jump into the wake and start accelerating forward. I'll just play it once more, if I can. So you see the laser, the fields start growing. Some of these electrons, you'll see two of them actually jump into the wake here, and they start accelerating forward. You'll see they actually start moving faster than the laser. And that's because there's a refractive index in the plasma, which causes the laser to travel something like 99% of the light. And so these electrons very quickly become relativistic. In this simulation, I think they reach about 200 MeV within about half a millimeter. And so we can do this, and we can accelerate particles to about a GeV. The next thing we need to do is we need to collide it with a laser coming the other way. And luckily Gemini is called Gemini because it has two beams, two identical beams. So one of them we use to generate electrons, and the second beam we come in from the other side in order to scatter from the electrons. And then we have to measure what we do is we put in a magnetic field that bends the electrons out of the way and allows us to determine the energy of the electron beam. And then we measure what the photon spectrum looks like as it comes out. And we do this with this cesium iodide scintillator block. So these are individual cesium iodide crystals arranged in an array. And we leave this outside the back of the chamber so that any hard X-rays produced by the electron laser collision will come in from the side, indicated by the yellow triangle, and they'll impinge upon the scintillator stack. And then if we view this from the side and look at all the scintillation light coming off, we can tell something about the energy. In fact, that's some real data overlaid across the scintillator, and you see most of the energy is deposited at the front of the scintillator with some of it extending through the back. So what do the results look like? I'll spin it round in that direction so you can imagine the gammas are coming from the bottom for the purposes of the displaying the data. So this is electron spectra. So you can imagine as the electrons are leaving the accelerator, they get hit by the laser, then they go through a magnetic field which bend them onto a plate. This is the plate showing the intensity of electrons along as a function of energy. These are not monoenergetic electron beams, unfortunately. We spent a long time trying to get them to be monoenergetic to make this to make the analysis easier. It didn't really work very well. But we tried to use these beams anyway. So this bright spot is around about 400 MeV. This hot tail is between 1 and 1.2 GeV electrons. And so each of these shots is where there's no colliding laser, and the top half is the cesium iodide stack, and there's not much signal on that either. So we turned on the colliding laser, and we saw these results. And you can see that for about half of the shots where we had the colliding laser on, we got signal in the cesium iodide detector. To explain why we didn't see it on every shot, you have to understand that the laser focus that's doing the scattering is about 2 microns in diameter. The electron beam itself is about 5 microns in diameter. And the jitter between the two is about 10 microns. And so trying to make sure those two things are overlapped and hitting every shot is almost impossible. And we're trying to come up with ideas of how we can post-process the data to understand what intensity the laser was when hitting the electrons. So the question is, okay, we're seeing some of these shots see signal and some of them don't. Is it statistically significant? So we plotted this graph. The orange line here is basically the background, and the orange dots are when there's no colliding laser pulse, and you can see that they scatter around a bit. But you can analyse what the scatter is there, and you can see that 3 sigma of this scatter is this red line here. And then turn on the colliding beam and see what happens, and you see the blue dots scattering around. And so you see there's a significant number of the shots, about half of them, where the increase in signal observed in the cesium iodide detector is bigger than 3 sigma. And so we reckon, we're pretty sure we've shot something. Until 2 days ago, we didn't think we could decouple how much energy was in the scintillator relative to how much energy was scattered from the electrons. But I spoke to one of our collaborators, Stuart Mangles at Imperial College. He says his postdocs have managed to pull out some extra data by simulating what any background signal might be. And it looks like if I was giving this talk next week, I might have been able to give you some really much better news. Unfortunately, at the moment, the latest is that we can't exactly tell what the intensity was when we were doing this scattering. So the good news is, if you get a laser that's 10 times as powerful, then your spot can be 10 times bigger in area, so about 3 times bigger in diameter, and then the whole experiment becomes a lot easier. And so that's the plan for the future. There has been work done on this already, in particular by the group at Queen's Belfast, and they did a similar experiment, and they couldn't hit the electron beam with the high intensity laser with much success either, so they put a diffuser in, and they made the spot about 10 times bigger or so, and they managed to see the photon spectrum appear to show intensity of about an E0 of about 2. And so they saw nonlinear Compton scattering, but not enough to see the radiation reaction effect. So the next thing is to reanalyze this data with the new information, which takes a lot of time. So this is some GEONT simulations which show how we expect the incoming photons to be scattered around by the scintillator. And you can see that you end up with some kind of energy deposit in front of the scintillator. The second thing you can do is you can say what happens if each of the photon spectra coming into the detector is monoenergetic. And interestingly, for this detector, you would normally expect the signal strength as you go across the detector just to decay monotonically as you go into the scintillator. Turns out if you go to above about 50 MeV, then the brightest signal doesn't come from the first scintillator, it comes from the second or third scintillator then. And that's what we're seeing. Because of that, we've got a good suggestion that what we're actually seeing is photons of above 20 MeV, and that's not possible with a linear Compton scattering event. So we're pretty sure we're nonlinear, and with this new information that we got this week, and this slightly more data analysis, we should be able to pull out something, we hope, indicating a scattering intensity of about A0 of 10. and hopefully we can show an effect on the electron beam as well that indicates we've seen radiation reaction, although I think that's maybe a little premature to say that for the moment. So we saw radiation above 5 MeV from a laser electron scattering event. Simulations at the moment signify an A naught of above 10, but that analysis is underway, and we think it may have just been completed this week, but not enough that I've looked over it and confident enough to present it yet. But the good news is that new facilities, these two dots here, that's Apollon and Eli NP, are going to exceed a petavolt power, and they're looking at focal spot about the size of 2, which means they should be able to reach intensity 10 to 23 watts per square centimetre. And we might be able to see these radiation reaction effects for the first time in a solid target experiment. And for now, we've seen lots of photon spectra, which possibly might give a possibility of a new short pulse photon source up to sort of hundreds of MeV, monoenergetic or broadband, depending on whether we use linear or nonlinear scattering effects. And hopefully, if we do some more of these experiments before Eli NP turns on in about a year and a half's time, we should be able to understand a little bit more about what these intensities are going to do. I'll just a list of all the people to blame for anything that went wrong in this talk, and thank you for your attention.
Thanks, Chris. Questions?
Yeah.
Antonio.
Simple question. In this interaction, I mean, what can happen is not a single interaction, in the sense that there are multiple repeat interactions.
Yeah.
And can this be the effect that you are seeing not in the first case of your, I mean, especially it sounded like it was distributed with a peak in the middle, the intensity of the interaction with your laser. Can it be a self-interaction of the object with itself? If you go back. Okay.
You're talking about the CSI
I'll
stack.
Yeah, yeah.
What?
The CSI stack.
The CSI stack.
Yeah.
There's a rather clear distribution in the middle of these objects, and it looks like. So I mean, is there any relation between the fact that all in the middle are the most colorful one? Is it self-interaction, or
So each of these is an individual shot taken about a minute apart.
Nothing. So it's just
So no. Now, interestingly, I think these are in time. So for example, I think this shot may have been taken around about 9 o'clock in the evening. This was about 9:10, 9:20, 9:30, all the way through to midnight. And of course, as well as having a problem where the spot jumps around a little bit, as the temperature of the lab cools at night, the whole laser system goes like this, and the spot slowly drifts across. And the fact that these 6 shots are all aligned together implies to me that there was a global drift of the spot rather than just the jitter. And actually, what was happening was this was drifting across the electron bunch. So yeah, so it's interesting. I think it's not an interaction thing, but it's probably systematic. The fact that all the shots that look good were beside each other. I don't think that's an accident.
So you just got the data from one day's worth of experiments. It wasn't repeated the next day with another set of dots.
We've got about 5 days of
So
shots.
do you see something like that then occurring on different days?
Well, yes. Our data, to be honest, is for us to get any data at all, the alignment has to be almost perfect. So it becomes very difficult to tell. So a small jitter, I mean, we'd need to look through all the data and see. Interestingly, there was a talk given a couple of weeks ago by a group from Oxford, and they looked at the both temporal and spatial alignment of the 2 Gemini beams as a function of time, and they saw this sort of they saw a slow rise in the offset, and then a quick drop, and then a slow rise and a quick drop, and this was occurring over the space of about 20 or 30 minutes, and they then went up to the final amplifier, and they took out all the temperature of the lab, and the lab is fixed between 20 and 21 degrees centigrade, and what happens is at 20 degrees centigrade it slowly heats up, and then the air conditioning kicks in and it quickly cools down and slowly heats up and quickly cools down, and when they overlaid their data with the temperature, it matched exactly with a 1 minute offset, which probably accounts for the amount of time it takes for the tables to react to the change in the air temperature.
Yay, theory!
I know. So yes, that I think it'd be
Your
interesting.
equations.
I know it's our equations are end up studying things like the so this guy presented some really nice data, and the conclusion was about the expansion coefficient of aluminium as a function of temperature when he's meant to do a laser plasma interaction.
Most expensive measurement of it ever.
Absolutely, absolutely, it's insane.
It's just a quick question about you mentioned measuring radiation reaction. What would be your signal for that experiment?
Well, you see, because this is the problem, right? What you'd like to see is you'd like to see this spectrum drop to here, and you
Short
can
form
kind
is a
of,
good one.
I've seen the data. If you kind of squint a bit, and then you look away, it kind of looks like that's
Yeah.
yeah.
So it's in the electron beam distribution at the end, basically.
Right.
That's
What you'd like to do is you'd like to measure the photon spectrum as well.
Yeah.
The problem is this is not a measurement of the photon spectrum, very realistically. I've funny story. I started working at Edinburgh with some nuclear physicists, and I said I had this problem of a large flux of photons, and they said, "Oh, it's fine. We've just developed these new rapid detectors that can detect high repetition rates of photons." And I was like, "Oh wow, how many photons can you handle?" And they said, and I said, "Because I've got about 10 to the 6 in 15 femtoseconds." And he said, "Oh, we're like 1 every 32 nanoseconds." And I was like, "Yeah, that's not quick." So how you actually measure the photon spectrum is an ongoing problem. We're actually still working at Edinburgh, and they're now thinking of new, slightly crazier ideas of how to actually get a spectrum out of this. Because actually the signal in the photon spectrum is much clearer than it is in the electron spectrum. It's much less ambiguous.
Yeah, that's what I was thinking.
But
But isn't that partly due to the fact that the electron beam is a bit messy? I mean, if the electron beam was monochromatic, then you just see the shift in the peak, right? It'd be very clear.
yeah,
But this is all assuming, nice collisions and nice beams.
right. This is the thing that even if you have a perfect collision, there will be 100% variation in the intensity the electrons see because the laser focal spot's smaller than the electron beam. We've got some simulations which, if you come to the HBL meeting, my student will present, which might indicate that we can do an on-shot compensation for the energy of the electron beam. But that's all top secret.
We're not videoing this or anything.
Yeah, exactly.
Chris, can you explain again the electron spectrum? What precisely is called? This is not a spatial.
This is space and space,
Okay.
but this dimension is real space, and this dimension is the spatial distribution of the electrons after they've been bent by an electric field. So the axis is somewhere up here. So these electrons have hardly been bent at all, meaning that they're the stiffest electrons, they've got a highest Gamma factor. And these electrons have been bent more. So these are low energy electrons and these are high energy electrons. And this is the spatial distribution. Another reason that you know that this is not nice is because see these wispy things. This is not what you want. These make good art but bad physics. It's the interesting thing about this is one of the reasons. So there's actually quite high background in all these, much higher than we'd expect. In fact, do you see anything here?
How would a close to ideal electron beam look?
It would be a spot here. That'd be a spot
High
here.
energy and
And monoenergetic and
Not
low
much spread.
distribution. Yeah. Now the question is, do you want it to be narrow or wide in this direction? That's debatable.
that depends on how targeted it is.
How collimated it is, exactly. So this indicates the divergence of the electron beam is about 5 milliradians. And this indicates the divergence of the photon beam is about 5 milliradians as well. Which is what you'd expect for a relativistic collision. Basically, it's the divergence of the gamma is tiny relative to the electron beam.
What's the distance between the CSI stack and the electron measurement? Just out of interest. It's like a meter of the order of a meter.
Yeah, metre or two. Yeah.
So I understand the challenge is basically to hit target.
Yes.
hit the target. So this has two. This has a spatial and a temporal aspect.
Yes.
Because you've got two pulses in two temporal pulses. So you get a time lag or jitter.
Yeah.
So you need a temporal simultaneous. How do you say? Simultaneity or something. And then of course also you need the spatial overlap. Which is easier to control? Can you comment? Or which is easier to control? Or
So-
any,
So it turns out that the temporal jitter between the two laser pulses on Gemini, the two laser pulses on Gemini have a duration of approximately 35 or 40 femtoseconds. The jitter between those two beams is the sigma. Standard deviation of that jitter is about 13 femtoseconds. So it's less than a third of the duration of the pulse, which is pretty good. You have to remember that one of the advantages of a head-on collision is, irrespective of the timing jitter, you'll still hit them. You might hit them at a slightly different intensity, you know, if the beam hasn't quite reached focus by the time the electron passes through. But if it's only 13 femtoseconds, that's about a Rayleigh range, and so you'd be within a factor of 2 maybe in the intensity that you think you are. And there's also an advantage in coming out of focus, because then you've got something bigger. But it's not clear. So the spatial jitter, I think they've now also put in an active compensator optic, which has piezo crystals in. And this is about, and it's got a CW beam that comes off it as well as the pulse beam. And as each shot goes off, so the shots are every 20 seconds, but even in the second area where they're 5 times a second, this mirror basically repoints the beam and compensates for that jitter. And they've got the jitter down from being about 10 microns as it was when we did it, down to about 2 microns, which is the size of the small pulse. So that's getting better as well. But the other question is, how do you measure that? You can put a camera in and look at the spot, but at some point you have to take the camera out and hope the two beams are still where you left them. As I say, these slow varying temperatures.
and are you going to redo it with the better specs now?
Hope so. If we get time, we'll try it. But I mean, last time a call was put out to use this laser system, there were 3 time slots available in 17 applications. So we need a new laser, which we're trying to get. Which will hopefully triple the number of experiments we can do if this new facility is approved.
Fingers crossed. Any other questions?
Can I ask a devil's advocate question?
Go on.
Just a brief one. So
You don't have to answer this, it'll be awful.
No. Cheers. So you talked about things going to 10 to 23 watts per centimetre squared with new facilities. What do you think is the major hindrance practically doing experiment at those intensities? For example, I'm guessing jitter and things like this are going to be more of a problem, not less of a problem.
Yes, yeah, that's true. So one of the good things about it is the effects that you see. We hit a relativistic electron bunch coming the other way, right? That's not a good way to do an experiment. At 10 to the 23 or 10 to the 24, even better, you can reach relevant chi values with a solid target. So now you've got 2 micron spot, but as long as it hits somewhere on that 3 millimeter foil, you still see the effect. So that's clearly, I mean, that's going to be a huge advantage. The second thing is, we might not push it up to a chi of 3 or 4 or 5. We might just keep it at a chi of 1 or 0.5, but we'll make the focal spot 4 times bigger.
Yeah.
So that should help reduce the instability of the pointing. Also, the way this facility's now been built, they basically poured a big sheet of concrete that's the size of 2 football pitches. When they built Gemini, they got the money for the laser, but not a new building. And so if this was the old Gemini area, basically what they did was they put some posts down and they put a mezzanine level that kind of stretched over above the target area, and they put the 2 arms of Gemini up there. And it was kind of funny, when it first opened, this arm of Gemini is fine, and this arm of Gemini went like this, because it was effectively an a cantilever, because it was fit. These squeezed into an old building. So again, it was about trying to get the best they could out of the money they had. With a purpose-designed building, I mean, the spec of that laser should have less of a jitter than Gemini. So it should.
It's a bright future.
Um,
That was nice.
On that bombshell, no more questions? All right, let's thank Chris again.